Hi, thanks for watching our presentation. My name is Johannes, and I'm really excited to talk about our paper One-Shot 3D Photography. Now, we used that title because the SIGGRAPH submission system is anonymous, but what the paper is really about is the Facebook 3D photo system, so that would have been a good alternative title. And this was a really big project that kept us busy for a good part of the last year or two, and for me it was really one of the most fun projects that I've ever been involved in. And that's in no small part to all the great people that helped make it happen. So I thank all my co-authors. So if we think back at how photography looked like over a century ago, it has really come a long way. This is one of the first pictures that was ever taken from the 1840s. And at that time, photography was a laborious and really expensive process. And the images just didn't look very good. But 100 years later, that has changed a great deal. So this image here was taken in the 1940s, and that was when color films were first introduced to the market. And then we go another 30 years later, and you can see even more improvement, but we're still talking about relatively low fidelity here. Now that changed with digital photography, which brought us really high fidelity, high resolution, and vibrant colors. Now, amazingly, today we can take photos that are just as good, if not better, with our cell phones. And this is just a snapshot here that I've taken recently. But how can this get even better? I think for plain 2D photography, we might be done. But there are other things we can do. And this talk is about turning your snapshots to 3D. So 3D photos still show moments that are frozen in time, just like regular photos. But they look a lot more alive than regular photos. And you can interactively explore them using parallax, and they look fantastic in a photo feed and make browsing a lot more engaging. You can also view them in VR, where they look really good too. You get stereo viewing and SIGGRAPH, head motion parallax. So this talk is about our Facebook 3D Photos feature, which lets you convert any image on your phone into a 3D photo. And this just takes a few seconds end to end, and you can directly share the result. Now, the best thing is you can actually try this right now yourself. So when you select a photo to post on Facebook, note that little Make 3D button here. So just tap that and your photo turns into 3D and you can share it. All right, so how does this work? What do we need to make a 3D photograph? Well, first we need dense depth. And one way to acquire depth would be using a dual lens camera. Many flagship phones have these, and this is what we relied on in the first iteration of our product. But most people just have regular phones with single lens cameras, and we want 3D photography to be accessible for anybody. So we turned to using machine learning and are actually now estimating depth from just a single color image using a CNN. And that works with any captured image, of course, and no special hardware is required. But just having depth for a photo is not enough. When we show a photo in 3D, we also need to know what's behind the objects that the camera was seeing. So one way to get that content would be by capturing multiple views of a scene. But this is tedious, and most people wouldn't want to spend that much effort for a photo. So we're doing this with machine learning as well. We're using another network to hallucinate content in image areas that were unseen by the camera. Now, there are a bunch of other non-machine learning steps too, and I'm going to walk through all of them in this talk. But first, I wanted to talk about some design objectives that we tried to achieve when we built the system. So we want 3D photography to be really easy, so even kids can do it, and it should work in a single shot. And we want 3D photography to be accessible for everybody, so it pretty much has to be on a cell phone and cannot require any special hardware. Because people are used to seeing their captures instantly now, the processing cannot take longer than just a few seconds. And it should be easy to share 3D photos, so we need a compact representation, a few hundred kilobytes at most. Finally, we want 3D photos to look fantastic, and we want interaction with them to be intuitive. And we believe that our 3D photo system achieves all of these objectives and is unique in doing so. Now, before I talk about the algorithm, there's another thing that I want to discuss first, because it's very central to our discussion, and that is the representation for 3D photos. So there's many alternatives here, but not all of them are suitable for our goals. In a light field, for example, we store many views of the scene and interpolate them to create novel views. And this enables representing very realistic scene appearance, but it has excessive storage and memory requirements, so it does not seem suitable for our application. Multiplane images represent a stack of frontal parallel RGB alpha textures, and this representation has been fairly popular recently because of its regular structured nature, which is kind of similar to a voxel grid, which makes it suitable for using in a CNN, but it is also not very storage efficient. So the particular representation that we use instead is called layered depth image, or LDI. And this is essentially an image where at each integer pixel position we can store one or multiple RGBD values. So the XY image coordinates are quantized just in a normal pixel grid. And each image coordinate corresponds to a 3D ray. The particular one that I've highlighted here contains 3 LDI pixels. Now, unlike the XY positions, the depth of an LDI pixel is not quantized and can take arbitrary floating point values. We also explicitly store the connectivity among LDI pixels in the structure. So every LDI pixel has exactly one neighbor in each of its 4 cardinal directions, or it has 0 if it's on an object boundary. Now, while dealing with this data structure requires a bit more engineering work, it has a lot of advantages too. So it's sparse, which means we can only represent the geometry that we need and nothing more. It has flexible topology, but behaves locally like an image, which is nice for algorithms. And it provides an inherent level of detail because it samples nearby geometry more densely. And then finally, it can be efficiently converted to texture meshes for rendering, which is very nice too. All right, so with this preparation, we're ready now to talk about our algorithm. Creating a 3D photo involves 4 steps. First, we estimate depth for the input color image. Then we generate extra layers of geometry. Next, we inpaint color texture on the new layers. And finally, we generate the mesh-based output representation. And all these steps together take only about 1 second or so on a phone, and the result can be viewed and shared instantly. And I'll now walk through each of these steps in more detail. Okay, let's start with depth estimation. So as I mentioned, we use a CNN to do this. In the paper, we describe a new architecture called Tiefenrausch. And the details are best explained in the paper, but roughly it comprises a unit-like architecture as in previous works, where each of the blocks is parameterized. And we use neural architecture search to find an instance with an excellent trade-off between quality, runtime, and memory. And we further use 8-bit quantized operators to reduce the model size and memory consumption even more. Please take a look at the paper for more details. Now, one question you might ask yourself is, why didn't we just use one of the many existing depth estimation approaches? There's been, in fact, fantastic progress in this area in the recent year or two, but most of these methods cannot be deployed on mobile devices because of too large memory and compute requirements. We show some extensive comparisons to previous networks in the paper. And so this table here is, in fact, from the paper and might look a little bit daunting, but what it basically shows is that the quality of our method is not too far off the best methods out there, while at the same time, it has an order of magnitude faster runtime, and it's even faster than the fastest other method we tried. And it has comparable memory consumption to the next best method. And our model size is only half of that of the smallest competitor. So our method achieves a really good trade-off for our particular application. Okay, so now that we've estimated the depth map for our input image, we're ready for the next step. And that is lifting the RGBD image to a layered depth image. And this is kind of trivially done if we naively connect all the surfaces. But in order to show some disclusions, though, we need to tear the LDIs open at strong depth discontinuities. Now, one problem is that in the estimated depth maps, the discontinuities are typically washed out over multiple pixels. So in the paper, we describe a simple filter that resolves this and turns all the discontinuities into step edges. Now it's easy to tear the LDI open at these edges, and we obtain this result here. The next step is to hallucinate content in parts that were occluded in the captured view. And we use a simple iterative growing algorithm that adds extra layers. Initially, we only create geometry, but in the next step, we inpaint color texture. So here, I'm marking all the surfaces that require inpainting with a checkerboard pattern. And if you think about it, a naive way to fill them would be to inpaint screen space, for example, just using a state-of-the-art CNN. But if you think about it, this wouldn't work so well in practice because, first of all, filling every novel view independently would be rather slow, and second, it would likely result in inconsistent results. So a better approach is to inpaint directly on the LDI structure, and then we'd only have to inpaint once and for all, and each view would be consistent by design. But how can we do that? So our key insight here is that locally, an LDI is like an image. And to show this, I drew a few squares here on different surfaces in the LDI. Because of this, we can actually well define a convolution operation on an LDI, and that's just what we did. So we can then use an architecture similar to the one described in the partial convolutions paper, and simply write custom convolutions and upscaling operators. And yeah, so this is how we essentially apply the network to our LDI. So one nice advantage of all this is that we can train our network entirely in 2D using regular images, but then apply the trained weights to do inference on an LDI using our custom operators. And this results in a really nice inpainting. So the last thing that we need to discuss is how to convert the LDI into a representation that can be efficiently transmitted and rendered. And this is the last step of our algorithm. So we decided to use a textured mesh representation because it can be efficiently rendered even on very low-end devices. And this brings two questions, how to generate the mesh and how to texture it. So let's start with the textures. Since the LDI contains many self-overlapping parts and it has complex topology, it cannot be mapped to a single contiguous texture image. So we thus partition it into flat charts that can be packed into an atlas for texturing. So we actually do this first because it enables a really nice trick to create a simplified mesh efficiently. And that is by doing the meshing in the chart domain. So here's one chart from that atlas you've just seen. And this is the detailed outline of the chart. And we first simplify the outline using standard polygon simplification techniques. And then we add some interior vertices and triangulate the polygon. And this can all be done very efficiently with low-level geometry textbook algorithms. And then finally, we'll lift the chart to 3D by projecting each vertex using its depth along its corresponding ray. And now we can just assemble all these 3D meshes into one, and we're done. This is the final 3D photo, and you've just seen all the steps of how it's been created. Okay, so let's look at some results. First, because our algorithm only uses a single color image as input, we can not only apply this to new images that we capture, but we can also apply it to historical photos and relive some moments from the past. Alright, that was pretty cool, and here are some more results that are more or less random photos captured by my co-authors and myself. Enjoy! So that's it. Thank you very much for watching our presentation. And one more time, if you're on Facebook, give it a shot right now. All you have to do is press the Make 3D button when you post a photo. Cheers.